Okay, this is part 2 of module 1. So this is big ideas. I didn't actually get to read that. So this example would be concerning a 3D shape and how to use or how to solve a mathematical model, as mentioned in the previous video, knowing what happens under the black box. So this investigation is about how temperature changes due to heat conduction. We've made an assumption that the bar just drawn before has steady temperature, so our temperature does not change over time, and it's one-dimensional, so the temperature does not vary other than, I think, across the x-axis. I think that's where the temperature only varies. So we have the y-axis, x-axis, and z-axis because it is a 3D shape. And yep, temperature would only change across the x-axis. So this is the principles and information that you need to consider when looking at the mathematical model. You need to make sure that you have all these assumptions down, so that working out would be easier and it will make more sense. So in the example, there is a control volume introduced. So just a well, I think it was called infinite or finite. I'm not sure which one, but infinite volume kind of. So the volume is negligible basically. And the pink rectangle, that represents the main focus of this investigation, but the control volume is what we're going to look at as an example. So that's what the rest of this video is going to be about. We're focusing on the control volume here. So again, you have your axes. As this 3D shape, you have your 3 axes. So because this 3D shape is basically negligible, we assume that all the axes turn towards 0. We don't assume that it is 0 because that will cause a problem in the framework. So whenever concerning calculus, we assume that it is 0 alone. So that will make the working out better. So let's consider the heat flow. So we know that it is across the x-axis alone. So therefore we'll use Qx as the variable to represent heat flow across the x-axis. So that is why the x is the variable value. So Q would represent the heat flow, and then Qx represents the heat flow across x. So as the heat flows through this cube, obviously as it goes through a certain distance, the heat will not be the same as how it was previously or at the beginning. So therefore there'll be a change. So we needs to leave the control volume square as it travels a certain distance along the x-axis. Yeah, so there will be a change that has occurred. So here's where we use differentiation to represent this change. We will do d is like dy over dx, but here we replace the y with qx to represent this change that has occurred, because it occurs along the x-axis and our main focus is the change of heat flow, and qx is the representation of the heat flow. Now, the dy dx only gives us the change in heat flow, but if we want to find the heat flow itself at the end, we will need to multiply the differential equation by the change in x. So then we know the distance that is travelled multiplied by the change, that's the change in x, multiplied by the differential equation, the x's will cancel out, and you'll have the heat flow at that point, or at the end, or the end face of the cube. So that's what's represented here. So moving on, this shows that the heat flow flowing out is slightly different from the heat flowing in or entering the cube. So that's the net flow out, and now we use Fourier's law. I spelt the name wrong, apologies for that. So we use this to relate to the temperature. This law or rule basically mentions that the heat flow is proportional to the temperature change. So basically the differential of the temperature, I don't think you say that, just the temperature change across that distance x. So here's a few examples of graphs showing how the gradient changes. So the higher, the right hand graph is a higher exponential graph, the left hand is a less steep exponential graph. So those are examples of what it means to have a higher gradient and lower gradient. So here the heat in, it will have a higher gradient because there's more heat at the end, but as the heat flows through the cube, it will lose energy, and therefore the temperature decreases. So this is the equation to represent the proportionality with the change in temperature and the heat flow. And as the temperature will decrease, of course there will be a constant with the proportionality equation, but the constant will be negative because the temperature is decreasing as it moves through the cube. Even though the cube's volume is negligible, as we are focusing on it now, then is not necessarily negligible. So I tried highlighting the equation here, and K is seen as the thermal conductivity. So that's the name of the constant for the thermal conductivity, and this equation is per unit area. So you'll multiply this by the area to get the, well, you could say either heat flow or the thermal conductivity across the area. And as the heat flows parallel to the x-axis, you will use change in z multiplied by change in y to find this answer. So here I'm describing what thermal conductivity, I think that was it, the name of the constant, and is basically the quality of the material. Thermal conductivity is the quality of the material you have. So if you have metal, that would have a different thermal conductivity to wood, for example. So that's why it is the constant. So that's just a short explanation. So finally, here you would use the second derivative to find the heat flow through all the faces of the cube. So as we're just given dt over dx, you can just use the, just add the squared on it and also multiply it by x, as that is the side which isn't included as well. Thanks for listening. For more content, please subscribe.